Welcome to the module Waves. In this unit we'll be talking about coupled oscillations. That means oscillations, for example, coupled to damping or to a driving force, or oscillations that are coupled together. So let's first look at damped oscillations. Now, as you've seen in previous units, we have described the harmonic oscillator as a sinusoidal oscillation at frequency omega equal to square root of k over m, with k being the spring constant and m the mass. Now, of course, these oscillations, they last until infinity, and this is not very realistic for physical systems. So we need to add the effect of damping. Now, how do we do that? We will add an effect of the damping to modify the amplitude, capital A, of this harmonic oscillation motion. And we do that with the following function. We introduce an exponent with e to the power minus c over 2m times t. So with c a constant and m the mass, this is positive number, and the minus sign takes care that for positive times this amplitude will decrease over time, as you can see in the function here. Then the total movement of the harmonic oscillator with the effect of damping is given by x of t is a of t, so the amplitude term, times the harmonic oscillator solution a sine omega t. So the final solution looks something like this. You will see that the oscillation starts with a high amplitude and then gradually diminishes over time. Now, for small damping, the frequency at which these oscillations take place is equal to the natural frequency square root of k over m. Now let's look a little bit more into this damping term. So we see that in this exponent there is a constant c and there's a constant m. Now, c is the proportionality of the damping with speed. And that means if c is large, then the damping is large and the oscillation goes rapid to zero. Now, if the mass m is large, then m is in the denominator. That means that the damping goes slower and that it takes longer for the oscillation to die out. Now, if you carefully look into the mathematical model, then you will also see that the damping affects the oscillation frequency. So the oscillation frequency is not only square root of k over m, but there is an additional term, c squared over 4m squared, that is dependent on the damping and on the mass. And this slightly changes the oscillation frequency. All right, so now let's look at driven oscillations and then deal with a phenomenon called resonance. In resonance, you will see here an example. We have a system with a natural frequency that we drive slowly at this natural frequency, and then the amplitude becomes bigger and bigger. And that means that it can lead to structural damage, for example, in this glass, or for example, in this example that you all have seen in this bridge. Now, how does this actually work? Now, for that we have to look a little bit into our initial assumption. So the harmonic oscillator was given by the balance of forces. M times A is equal to the sum of all forces is minus kx, which is the spring force. This led to the original harmonic oscillator solution. Now, when we start driving it with the force, we have to, of course, add this to this balance of forces. So in this case, we get m times A is equal to minus kx minus f0 cosine omega ft, where omega f is the driving frequency and f0 is the force with which we drive this harmonic oscillator. Now, if you solve this, then you'll see that the motion of the oscillator is not the simple harmonic oscillator anymore, but it's still an harmonic motion. It's harmonic with a frequency omega f. It has a phase shift phi that depends on this driving frequency omega f, and it has an amplitude that depends on this driving frequency omega f. Let's look at this amplitude term that depends on omega f. So here you can see this a of omega f. It's a big function here, and it's plotted here on the right-hand side. And let's look at a little bit more in detail. So it's proportional to f0 over m. That's essentially the acceleration I give it whenever I drive it. Now, secondly, there's a term in the denominator, omega f squared minus k over m, and that squared, that can become 0. If that becomes 0, then essentially we're in the condition of resonance. That means that omega f squared is equal to k over m. So the driving frequency is equal to the natural frequency. And then the amplitude, of course, becomes large if this term is 0. Now finally, there's also a second term in the denominator, c squared omega f squared divided by m squared, and that is due to the damping. And essentially that restricts the amplitude for not going to infinity. Now, of course, this is all the theory about the driven harmonic oscillator, but a very simple model is, of course, a child on a swing. The child on the swing has, of course, a natural frequency going back and forth, and every time it's coming towards you and you push it. And that means that you're driving it at its natural frequency. And also that means, of course, that the amplitude becomes bigger and bigger. And if there were no friction, of course, the amplitude becomes very, very large. All right. Now we have looked at the driven harmonic oscillator. Now let's look at other types of coupled oscillations. So what happens if we add two oscillations together? Now, we will look at this in a bit more detail by representing a harmonic oscillator being a motion of a vector in the 2D plane. So for example, our x1 of t is a1 sine omega t plus phi 1 can be represented as the x-coordinate of a vector moving in this xy plane. Because for phi 1 is equal to pi over 2, the sine becomes the cosine. So the harmonic oscillation can be represented by a vector where the phase of the vector, the starting point of the vector is essentially the phase of this sinusoidal movement. The amplitude of the harmonic oscillation is essentially the length of the vector, and the frequency of the harmonic oscillation is the rotation speed of the vector in this plane, as you can see here in this representation. Now, what happens if we add multiple periodic functions together? So what happens if we take the sum of two harmonic movements? Well, it's not clear a priori what it is. But if we look at this graph, we will see that this one vector starts to move, and then the other vector starts to move as well, and at a certain point it catches up with the first vector. And that means that this pattern will repeat itself over time. Now that means that the sum of two harmonic functions is also periodic. So let's take a look at a few examples. So let's first take two harmonic functions. We take them to have the same amplitude, the same frequency, and the same phase. Now, if we do that, it's just a simple matter of trigonometry just to add them two together, and we will see that the resulting oscillation has an amplitude that is twice as large as the original oscillation. This is what we call constructive interference. The two oscillations add up together to a larger oscillation. Now, secondly, we'll look at another type of addition, and that is with one oscillation being pi radians out of phase with the first oscillation. Now, if you take the sine of an argument plus pi, this essentially changes its sign, and therefore if you add these two oscillations together, a sine omega 1 of t plus phi 1 and a sine omega t plus phi 1 plus pi, you essentially get 0. And this is what is called destructive interference. The two oscillations entirely cancel each other, resulting in a sum that is actually 0. Now finally, if you add two oscillations together that have the same phase and the same amplitude but a different frequency, then you get a phenomenon called beats. And you can, of course, use your trigonometry to derive this entire function that is being shown here. But what it essentially means is that you get a product of two harmonic functions, a cosine and a sine, with the cosine having a difference frequency, omega 1 minus omega 2, and the sine having a sum frequency, omega 1 plus omega 2. So the sum frequency leads, of course, to a high frequency repetitive pattern, and the difference frequency leads to a low repetitive pattern, and these are multiplied. So you get a pattern that is shown here in this graph where there's a certain slowly varying envelope around a highly oscillating frequency. And this is what is called beat, and is, for example, important when you want to tune your guitar. Now, coupled oscillations play a big role in all kinds of physics. For example, in optics, where we illuminate, for example, a slit. There you can have interference patterns that are essentially additions of oscillations that lead to constructive and destructive interference. Also in mechanics, you can, for example, have two oscillators that are coupled together, where one oscillator transfers its energy to the other oscillator and back and forth. This leads to a phenomenon similar to the beat pattern that I showed you. And also in chemistry, the coupling between the oscillations of the different atoms in the molecule will lead to different kinds of oscillation modes that are, of course, important to understand the vibrations in the carbon dioxide that play a large role, for example, in the greenhouse effect. So finally, in summary, I've described the harmonic oscillator with the effect of the damping, with the effect of the driving force. And also when we couple different oscillations together, we have discussed the effects of constructive interference, destructive interference, and the formations of beats.